Okay, we're going. So in this problem, we're asked to show that if the order of A is infinite, then if we look at the set of all the powers A to the m for all integers m, that these are all distinct elements of the group.
Okay, so how do we want to do it? Do we want to prove that they're distinct, or argue by contradiction?
I guess, how do you show that two things are distinct? You're showing they're not equal. So it sort of has a not in it, so it's sort of natural to do it by contradiction, or contrapositive, I suppose.
Okay, so argue by contradiction or contrapositive?
I think it's really contrapositive.
Okay, contra.
We're going to imagine they're not all distinct, and then we'll show the order of A wasn't infinite.
Suppose they are all not distinct, so that means that there exists m and n in C with m different than n, such that a m equals a n. So two of these things indexed differently are the same.
Okay, this reminds me of the problem we had earlier, where we had something exactly like this. Were there any extra hypotheses we needed there?
Well, let's check. It just said that one of the integers was smaller than the other, but there's always gonna be
If they're
one
not
that's
equal
smaller
to each other, then one of them is
than
smaller
the
than
other.
the other.
So, yeah, it just said that in that case.
Okay, so let's
So this was part 2.
That m is the smaller one. I think that's what we had before. We know one of them is smaller. I guess it is without loss of generality.
So by part 2, we know that the order of A was what?
We know that the order of A is at most n minus m.
Okay.
But I guess if the order of A is at most n minus m, the order of A is not infinity. Because infinity is definitely not less than n minus m.
So we reach a contradiction. Or, I guess, no, we're arguing by contrapositive. We
the
reach
order of A
that,
is finite.
then it's
That's what
finite,
we wanted.
which is, negating this.
Yes.
All right.
Okay, so what's the next thing we're going to talk about?
Show that the order of an element A is equal to the order of the subgroup generated by it.
Well, that would certainly be nice, and the notation would make some sense. I'm supposed to show that the order of the element A is equal to the size of the subgroup generated by A, which I guess looks like this.
Okay. Should we try to prove that one is less than the other? Since we're comparing to natural numbers, should we go both ways?
I guess we can try to go both ways.
Okay.
Which is the easier way, do you think?
I think the order of an element is a concept that's easier than the order of a subgroup.
Okay.
Because you just take powers of that element. So I would.
So we want to go this one being smaller?
Mm-hmm. So, okay, the order of A is an element n, if and only if A to the n is E, but also A to the m is not E for all m less than n. And
Where
bigger
m
than
is
0.
bigger than 0.
Okay.
Okay.
So we need to find at least n distinct elements if this happens inside of this subgroup?
Well, I guess I can sort of imagine what they look like. I want things that look like, what, a and a squared and a cubed. And if I just keep going like this, I guess they go all the way up to a to the n, which is e.
Okay, so first question, are these distinct? Like,
Well, I hope so. So I guess what would happen if they weren't distinct?
And n is not the order, right?
Then n would not be the order, because then we'd be in the situation that we had before,
part 2,
two different parts that were equal to each other.
and then the order would be
And we
less.
could do the division algorithm and get a smaller order. So I think these all have to be different from each other. And there's n of them.
There's 10 of them, and all of them are elements of the subgroup, right?
Oh, that's right. They're all inside the subgroup, because the subgroup is in particular closed under multiplication.
So that means that we've proved that this is bigger or equal than n, which was the order of A.
Great, so that's
So
the
we
one
got
direction we wanted.
All right,
All
now
right,
go the other way.
so we want to show, I guess, that there aren't any extra elements in the subgroup. We found n of them, we need to know there aren't any more.
Oops.
Oops.
Okay, should I?
Well, okay, so like what is in my subgroup? My subgroup is defined to be just like all powers of A.
So we gotta show that every other power of A is one of these.
Is one of these.
So maybe let's write that down.
Yeah, let's write that down. I think we can write right here.
Oh yeah, there's a lot of
There's
space.
so much room.
Okay. So, now we're aiming to show this. So, well, really equality, right?
Yeah, but we already have the other inequality.
So like we need to show, okay, let me be a little clear. A, by definition, if we're using multiplicative notation, is all the powers of M. So what we need to show is that if we have something that looks like this, then we can find some k and one of the ones that Oliver was using, k in 1 through n, and we need to do this for all m and c, because that's proving that any element in this subgroup, sorry, I should have written this as brackets, any element like this is one of these, which there are n of them. So that way we'll conclude our proof. Okay, so how will we find it?
Well, it sort of reminds me of when we were doing modular arithmetic,
Me
like mod n. And I kind of regret maybe writing them this way. Maybe I would have preferred to like have a to the 0 equals e over here. And gotten rid
Okay,
of
that
this
also
one.
works. I mean, this set has an element
Because-
as well.
Yeah, this was the sort of stuff that I tended to get thinking about modular arithmetic. So maybe
That's
that would
true.
be better
Mhm.
if I relabel them like that. Well, I guess before we were trying to do the division algorithm. I think if I take a to the m and I divide it by n, what should happen?
So you're dividing.
So let's use the division algorithm on m. Okay. Then m is going to be n times some quotient plus some remainder. And our remainder's got to be at least 0 and smaller than.
And minus 1. So in this that we have here.
Smaller than or equal to n minus 1, I think.
Yeah.
Okay, well if I do this, then I have a to the
That's
m,
the way that we usually write it. It's like you were saying. Sorry.
but I think actually yours might be,
Ah.
it's the same. Okay, if I rewrite it like this, then just like before, this is a to the n to the q times a to the r.
Oh,
A
and
to
now
the n
and
is
what's the
already the
order?
identity. So this is just the identity to the q
did this stop?
times a to the r.
This is no.
No, wake up.
Ah!
Ah!
Wait, what? I mean, the camera light is still on. So maybe it's just.
Oh my god.
Oh, it's still going. We're still going. What a great video. We have this is a to the r.
Okay.
Oh, and a to the r is one of the things we wanted.
Yeah. I mean, I use the letter K, but
what's
it doesn't
retroactive,
matter.
They make it an r. There's an r all along.
Okay. So what we have shown, I feel, is that this is the set a to the 0, a to the n minus 1, which has n elements. We showed that they were distinct. So, and n was the order. So we're done. All right. Screaming. This is